Okay, welcome to the third part of our video series on single input production functions. We're going to talk about calculus here for now. We've been working up to getting to the calculus-based approach. And so the first thing we're going to do is go over just doing derivatives in calculus, and then we'll get to the calculus of optimization, and then we'll apply it to our farm management problem here. In this class, we're going to keep the calculus very simple. For those who've had it, it's nothing more than quadratic equations. And so all of our production functions are going to be quadratics. So some function output Q is going to equal f of x is going to be some number A plus some number B times the input x plus some number C times the input x squared. First derivative is going to be the slope of the production function, the marginal product. You have three different notations people tend to use. I tend to use the dy dx or dq dx in this case. That's Newton's system. The f prime of x is the other one. Leibniz invented that one, and we'll get into multiple derivative, partial derivatives, and we'll use f sub x of x. Newton and Leibniz both invented calculus. Newton was much younger. Second derivatives then are going to be put the d squared y dx squared or d squared q dx squared f double prime of x or f sub xx, depending on the notation you want to use. So you get a sense of that's when you use this notation. I want to do a quick review of the derivatives, focusing in on quadratic equations. So first thing is a constant function. So normally you would think of a constant as x is your horizontal axis and y, or in this case q, is the vertical axis. So q equals 7, or some number like k, whatever it is. It's just a horizontal line, flat. Everywhere, no matter what x is, output q is 7. What's the slope of that? 0. So the derivative of a constant is 0. There's no slope. Power function. When you have you think of some number, you got x, and you got a power, you got a coefficient in front, and you got a power, an exponent up there. So think of q equals f of x is a times x to the b. So a is some number, and x is raised to some power b. B is only going to be 0, 1, or 2. You can rate, and then the number in front will just be our coefficient. The first derivative is just going to be that coefficient a. You bring the exponent down as a coefficient in front there, and then x to the b minus 1th power. And so we'll do a couple examples, and this is the extent of it in the class, but that rule applies broadly to cubics and quartics and everything else. So q equals f of x, let's say it's 7x. Well, that's really 7 times x to the 1th power. So what's the derivative? It's 7. Bring the exponent down, that's the 1. Then x to the 1 minus 1 power. Well, that's x to the 0th power, that's 1. And 7 times 1 times 1 is a 7. And so derivative of 7x is 7. And so the way to think of it is draw a line coming out of the origin, going up with a slope of 7. So what's the slope of a line with a slope of 7? 7, or whatever the number out in front is. The other one is quadratics there. And so we got 3x squared in this example on the slides. And so the derivative will be the 3 will stay there, the a in front. You'll bring the 2, the power down, and then you'll take x to the 2 minus 1, which is x to the 1th power, or just x. And so then what you get is f prime of x is 3 times 2 to the x, or 6x. So that's going to be the extent of our derivatives here for power functions. You got a constant, a linear term, and a quadratic term. And we've done the derivatives of each of those. And then now let's add them all up. The derivative of a sum of functions is just the derivative of the sum. The sum is the derivatives of each of the pieces. So you've got a q equals 3 plus 5x minus 0.1 x squared. What's the derivative of that function? It's just the derivative of each part added up. And so what's the derivative of 3? 0. We've done that one. That's a constant. What's the derivative of 5x? We've done that one. It's 5. And what's the derivative of minus 0.1 x squared? Don't forget that minus sign. You bring the 2 down, it's just going to be minus 0.1 times the 2 from the squared term times x to the 1th power, or just x. And so the derivative of that 3 plus 5x minus 0.2 x squared is going to be 5 minus 0.2x is the final part, is when you reduce it down. So there are your derivatives right there. And that is just a mathematical way to get to the slope of the functions. So done a quick review of derivatives. Now let's do a think break here. We'll take a pause. You should sit down, grind these out, work them through, and you're going to take the first and the second derivatives. All the second derivative is the function you get left over with, take its derivative again with respect to x. And so, for example, that q of x, number 1 there, first take the derivative, the first derivative, you'll get an equation. Now take its derivative, that's the second derivative, the derivative of the derivative. And then the next one is pi of x, and we'll come back to that one too. That'll be our basic model here of the whole profit decision the farmer faces. So go ahead and do these two, and then we'll come back to the think break. I'll go over the answers with you. Okay, well, welcome back. Q of x then is 4 plus 15x minus 7x squared. Let's take the derivative of it. Well, the first derivative is just going to be the sum of each of those parts, take those derivatives. And so the derivative of 4 is 0. So that's gone. The derivative of 15x is just 15. And then you get that last part, minus 7x squared. Well, it's the minus 7, bring the 2 down, and then take it times x to the 2 minus 1, or just x. So what you get is 15 minus 14x. Second derivative is the derivative of the derivative, and that's just going to be the derivative of 15, which is 0. And then what's the derivative of minus 14x? Minus 14. And so there's your first and your second derivative. When you got a quadratic equation, that's the way it works out. The first derivative will be a linear function. The second derivative will be a constant term. Let's do pi of x here. I gave you a longer equation, 2 times something in parentheses, 5 minus x minus 3x squared, minus 8x minus 15. Well, we could multiply it all out and then combine like common terms, and you'll get another quadratic equation like we did up above there. I'm going to do it in this form, though, without doing the multiplying it out and recombining like terms. So the 2 will stay out in front. So we just take the derivative of the part inside the parentheses now. 2 times the derivative of the part inside. Well, what's the derivative of 5? That's 0. So we're not going to write that in. What's the derivative of minus x? It's just going to be minus 1. We always got to be careful on those minus signs and those ones, and that are, we traditionally don't write them down. So 5 minus x minus 3x squared, that derivative is 0 minus 1, and then that minus 3x squared is going to give us the derivative of 6x with a minus sign in there. Don't forget the minus sign. So what's the derivative? It's minus 1 times, or plus, or minus 6x. And then that 2 is going to stay outside the parentheses all the time. So it's 2 times minus 1 minus 6x. That's what that first derivative part there is. Now we got the last two terms. The minus 8x, the derivative of that is minus 8, and then the derivative of minus 15 is 0. So now we'll combine our terms, and you're going to get minus 10, which is just 2 times minus 1, or minus 2, and then the minus 8 gets you minus 10, and then the 2 times the minus 6x gives us minus 12. So we get all that work to get to the final first derivative is minus 10 minus 12x. Take its derivative, the derivative of the derivative is the second derivative, and you're going to get, again, a minus 12. And again, the derivative of a quadratic equation, that pi of x is a quadratic equation. We just haven't combined the like terms. Is a linear equation, then the derivative of the linear equation is a constant, in this case, minus 12. All right. So now let's talk about the calculus-based approach to finding optimal input use. What we're going to do is create a mathematical model of the farmer's problem here. And essentially, you're assuming the farmer's trying to maximize profit, which is, we're going to describe profit as revenue minus cost. How much money you bring in minus the cost you spent to get that revenue generation. So what is revenue? Price times output. You're doing corn, trying to figure out how much fertilizer to use. It's the price of corn times how much corn you harvest. Or if it's milk, it's how much feed you, it's the price of milk times how much milk you produce. Then you got these costs. What are they? You're going to split them into the input cost to buy the fertilizer if you're growing corn, to buy the feed if you're producing milk. And then there's going to be some other fixed costs running around there. So the way we write this then is pi is equal to P times Q, price times the output, minus the cost of the input R, that's the input price, times however much input you buy, X, minus some fixed cost K. Or then the key is to make that, take the Q out and put in the production function f of x. And so what you get is you get the price of output, P, times f of x, minus R times x, minus the K. Learn that model. We're going to use it a lot. We've highlighted it in blue so it stands out, bolded the last part, and what you're going to see is we've already been playing with functions of this sort. Problem 2 in the think break was exactly this functional form and this setup of the profit function. So let's find the x to maximize profit as a function of x equal to P times f of x minus Rx minus K. Calculus-based approach is the first thing you do is take the first derivative and set it equal to 0. That is the first order condition. And then you're going to take that first order condition and solve it for the x. Well, we've kind of been through some of this notation already. So what's that derivative of P times f of x minus rx minus k. Well, you take the derivative of P times f of x is going to be the price P times the derivative of f of x. Well, we call that the marginal product, f prime of x. Then r times x, doesn't matter what r is, you take the derivative of minus rx with respect to x, you're going to get to minus r. First order condition is you set that derivative equal to 0, and that gives you P times f prime of x minus r equals 0. Rearrange, put the r on the other side, and you get P times f prime equal to r. Well, that is going to be P, the price of output, times the marginal product, f prime of x, equal to the price of input, r. We've seen this already. Go back, look at those partial budget analysis, and we did it when we divided by the delta n. We got to that's exactly what we had there. We had the price times the marginal product. And you found where it equaled to the price of the input. P times the marginal product is something we call the value of the marginal product, what you got if you sold the additional output you produced with a little extra input. That's your marginal product. You add a little more fertilizer, you get a little more corn, that's your marginal product. That's a little more corn, it's the marginal product. Then you sell it. What's it worth? It's the price of the corn times the little extra corn you got. Value of the marginal product. First order condition means keep increasing the input use, the use of the input x until the price times the marginal product equals the price of the input, or until the value of the marginal product equals the r, the input price. Go back to your partial budget analysis. Keep increasing it until the net benefit is equal to the net cost. That spot is going to identify the optimal input use. That's all we're doing here. So how do we do some of this a little more formally? Choose x to maximize some function g of x. First order condition is set g prime of x equal to 0 and solve for x. There may be more than one x. Not going to be the case in this class, but you could easily have types of functions that do have more than one. So we call these potential solutions x star. You have to go through them all and figure out if they're a maximum or minimum. How do you do that is you have to go to the second order condition. So there will be multiple, possibly, not in this class, but potentially there are multiple solutions that give you a spot where the slope is 0, where the first order condition is satisfied. Then we use the second order condition to see if it's a maximum or a minimum. And that's what we're going to go to. The second order condition is you take the second derivative of whatever your function is, g double prime of x, and you plug each x star in, I should say. If it's a maximum, the second derivative is 0. If it's a minimum, the second derivative is positive. The way I always think of this is the second derivative is the derivative of the derivative. It's the curvature of the function. If it's convex, it's a positive. The ends of the curve point upward. That's a positive second order condition. And if it's a concave, ends point negatively. They point down. That's a maximum. And so if it's convex, they point up. If it's concave, they point down. Caves are under the ground. You go down into a cave. If you want to think of it that way, a concave function looks like the door to a cave. You think of it that way. But a negative curvature is concave. It's a maximum. There's a top to it. Where it's a convex, it makes a cup, and the ends point upward and positively, and it's a minimum. So you have to check the second order condition for each of your points. So while you're doing is your first order conditions, you're setting the first derivative equal to 0 and solving for x. You're finding the spot where the objective function is flat. These are candidates for a minimum or a maximum. Then the second order condition checks the curvature at each candidate solution to see if it's where the slope is equal to 0. Is it a curve downward for a maximum, or is it a curve upward for a minimum? Potentially, there's an inflection point where a bench where it comes up and makes a flat spot and continues back up. A saddle point is another term for these. These saddle points they occur. We're not going to deal with these technicalities. We're generally I'm not going to give you ones that have these problems, but you get the sense of all I really want you to know is that second order condition, it should be negative for these maximization problems, which is for a concave function. So let's do an example. There's a quadratic equation. Choose x to maximize g of x is minus 5 plus 6x minus x squared. What's the first order condition? Find the first derivative and set it equal to 0. So what's the first derivative? The derivative of minus 5 is 0. There's no change. No matter what x is, minus 5 is always minus 5. The derivative of 6x is 6. The derivative of minus x squared is minus, bring the 2 down, so minus 2 times x. So there you see that there. 6 minus 2x, now set it equal to 0. 6 minus 2x equals 0. Do a little algebra there. Put the minus 2 on the other side. 6 equals minus 2x. Divide both sides by 2, and you get x equals 3. So is this a max or min? Or is it a saddle point? And how do you know? Check the second order condition. So what's the second derivative? The derivative of the derivative. You go to first order condition, take its derivative. The derivative of 6 is 0. Derivative of minus 2x with respect to x is minus 2. It's always negative. And so you've got a nice little parabola. No matter where you are in there, no matter what x you have, it's always a negatively curved function. So you satisfy the second order condition for a maximum. So negative satisfies the second order condition for maximum. What's the value then? At x equals 3, what is g of x, the function we're trying to maximize? Just plug the 3 back into the parent function way back at the beginning. Minus 5 plus 6 times 3 minus 3 squared is minus 5 plus 30 minus 9. You get, minus 5 plus 18 minus 9, you get 4. So that's example 1, nice little simple. Here's the graphics of it. You get a parabola, that's the g of x. There's the first order, the first derivative, g of x, g prime of x. It crosses right here where it's 0. That's the spot where the slope is 0. That's also where the slope function crosses the 0, the y-axis, or I'm sorry, the x-axis. And so it's sort of seeing there's, what is it at that point when x equals 3, output is 4. And so you can see all those numbers are right there. Let's do another example here. Same thing, another quadratic equation. G of x equals 10 minus 6x plus x squared. Take the first derivative and set it equal to 0. What's the first derivative? The 10 doesn't matter, and so you get derivative of minus 6x is minus 6. The derivative of x squared is 2x. Notice there's no minus sign. This time it's 2x. So minus 6 plus 2x equals 0. Do a little algebra, and you're going to get x equals 3. Put the minus 6 on the other side, and divide both sides by 2. You can get x equals 3. Is this a max or min? How do you know? Check the second order condition. Take the derivative of the derivative. So go back to the first order condition. Take its derivative. What do you get? The derivative of minus 6, nothing. But the derivative of 2x is 2. So no matter where you are on there in terms of x, the curvature is always positive. It's always pointing upward on the curvature. So that's not a maximum. It's actually a minimum. And what's the value there? Just plug the 3 in. You can do g of 3 is equal to 10 minus 6 times 3 is 10 minus 18 plus 9, and you're going to get 1. So here's the graphics of this one. The red is the parent function or the objective. Where's the slope 0? Right here. That's at x equals 3. There's the first derivative. You can see it crosses the axis at x equals 3. What's the level? Right there, it's at 1. If you plug in 3 into the red function, it comes out as 1. So what value maximizes this function? In positive infinity or negative infinity. The maximum never happens. It just keeps going up and up and up. So there really isn't one. It's a poorly defined problem. That's why you check the second order condition. All right, so let's do an example here. This will be another think break, and this is sort of like where we've been heading at this whole time. When x satisfies the first order condition, does this x satisfy the second order condition for a maximum? Then what is the profit at this x? So go ahead and do this problem. We'll come back. So I would recommend sitting down, take that pi of x, take its first derivative, set it equal to 0, solve for x, and then check the second order condition by taking the derivative of the first order condition, and then plug the x back in and get your profit. So go ahead and do that, and I'll meet you here in a few seconds or a few minutes. Okay, we'll do the first part here. Choose x to maximize. There's our long parent function. Looks very much like think break 4, the derivative we did there. So what x satisfies this one? You got to take the first derivative and set it equal to 0 and solve for x. So let's do the derivative here. We'll leave the 10 out there and just take the derivative of the inside part here. So what's the derivative of 30? 0. What's the derivative of 5x? 5. And then what's the derivative of minus 0.4 x squared? It's going to be that minus 0.4. You're going to bring the 2 down, and then x goes down from x squared to x. And so you get minus 5 minus 0.8x. But 0.8 is 0.4 times 2. And so the key there is you get the linear term 5, and then you get the linear term. You get the constant term, I should say, and then the linear term minus 0.8x. The 10 stays outside there, so you get 10 times, in parentheses, 5 minus 0.8x. Now, take the derivative of those last two parts there, the minus 2x and the minus 18. Derivative of minus 2x, minus 2. What's the derivative of minus 18? 0. So now we have our first order condition there, the third line. 10 times the quantity, 5 minus 0.8x, minus 2 equals 0. Now we do our algebra here. Take that first derivative, set it equal to 0. We've done that. Now let's do our algebra. Multiply the parentheses out and move the 2 to the other side. So 5 times 10 is 50. 10 times 0.8 is 8. So 50 minus 8x. And then minus 2, switch it to the other side. And then you bring the put the 2 back over there and put the minus 8x on the other side, and you do a little more algebra, and you get x equals 6. Does this x satisfy the second order condition for a maximum? Well, we got to take the derivative of the first derivative, we get the second derivative, and then you want it to be negative, pointing downward of the curvature. So what's our first derivative there? Is 10 times minus 5, or 10 times 5 minus 0.8x minus 2. Take the derivative there, and you're just going to get that 10 times this minus 0.8x. Well, that derivative of minus 0.8x is minus 0.8. Take it times the 10, you're going to get a minus 8. So no matter, if you want this one, you might want to multiply it out just to keep everything clear. If you multiply it out, you got 50 minus 8x minus 2. Well, the derivative of that is, you can see the minus 8 is where it's going to pop in there. The 50 and the minus 2 doesn't matter. So x equals 6 is a maximum. The second derivative is negative. It points downward. So the x equals 6, the spot where the slope is 0 is a max. Now, what is profit at that point? Well, let's take that x equals 6 and plug it back into our objective function way back at the top. So 10 times the quantity, 30 plus 5 times 6, 30 plus 30, minus 0.4 times 6 squared. And then you get minus, there's a parentheses missing on the slide here. And then you get minus 0.2, I'm sorry, minus 2 times 6, minus 18. There should be a parentheses after the, so the 10 is times this as well. So 10 times 45.6, that's, where's that 45.6 come from? It's 30 plus 30 minus 0.4 times 36 times 6 squared, or 36. That's 45.6. That's the multiplication of that inside part when x equals 6. And then you get the minus 12 and minus 18. 12 is 2 times 6, and minus 18 is a constant. So 456 is 10 times 45.6 minus 30, which is minus 12 minus 18. That's your minus 30. And you get 426. So what you got there now is x equals 6 is a maximum, second derivative is negative, and what's about the value of the profit at that point? 426. What you can see there, if you actually, you can see this is your really a profit. It's the price of output is 10, there's your production function, and there's your price of the input is 2, and there's your 18. And you calculated the output is 45.6. That was the inside part. You took it times 10, and you figured out your how much everything, what your profit was. So suppose output price is 10, input price is 2, and fixed costs is 18. That's what we just did. So we got our profit relationship is price times output minus R times X. That's the cost of your input. R is the input price times however much you use. And you get some fixed costs running around. Well, there's our profit function. That's our general story. We just did a production function, f of x equals 30 plus 5x minus 0.4x squared. And then we had an output price of 10, input price of 2, and a fixed cost of 18. That's what Think Break 5 just was. There is our profit relationship. Profit as a function of x is the price of output, P, or 10, times our production function, 30 plus 5x minus 0.4x squared, minus the cost of the inputs, which is minus, that's 2, the price of the input, times however much input you use, x, minus 18, which is our fixed cost. We just solved this problem. We did the calculus and then did the algebra. You got x equals 6. It's a second order condition satisfied. It's a maximum. You plugged it in. Output was 45.6 and profit was 426. So we've kind of done the whole problem here. That's where we're getting to in this whole section of the course. So if you go through, I've done the solve here and everything is all laid out again. And the part I want you to really notice is tying it back to everything we've done before. There's P, 10. There's our marginal product, 5 minus 8x. That's the marginal product. When you put and then minus 2 is the price of the input. When you put the minus 2 on the other side, you got the value of the marginal product. 10 times 5 minus 0.8x is equal to the price of the input, 2. Then you're just doing algebra after that. Value of marginal product equals the price of the input. You just figure out what the x is. Before, you looked on the table and saw where did this happen. Now you do algebra to figure out where it happens. What level of x makes the value of the marginal product equal to the price of the input? You don't look in the table, you do the algebra to do it. You could also do it 5 minus 0.x equal to 2 over 10. Then you get marginal product equals R over P. Same story. All you're doing when you do the algebra is setting the value of the marginal product equal to the price of the input. What x makes that happen? And then you plug your 6 back in. You go through the effort here, and you can see Q is 45.6 and profit is 426. So that's just, I've said it multiple ways. It's laid out here. You can see it. So I just want to make sure you get a sense of where we are here. This is the calculus-based approach to farm management on optimal input use. And we'll go through eventually two inputs, and then we'll go through a production tools that do this for you. So kind of in summary, for single input production function, condition to find the optimal input use. Where is it? When the value of the marginal product equals the price of the input, VMP equals R, or you can do it as the marginal product equal to the price ratio R over P. Same thing. We talked about that. We've done it with the table. We've done it with calculus, and the algebra will help you find that X. What does it mean? We talked about that. What does it look like graphically? We talked about that. Then you want to know how to use that condition to find the optimal input use. Done it with the table, and we've done it with calculus. And so all we have to do after this is go to two inputs, and then I'm going to show you there's production tools out there, graphs or tables you can look them up in, or little online apps or on your smartphones to actually do all this. And we'll see they use calculus and they use quadratic equations.